All right, guys. First, we'll talk about NumPy. So NumPy is a high-performance, multi-dimensional array manipulation and numerical computation library. And it derives its reliability and remarkable performance from Fortran roots. So I'll give you an idea. So you guys are looking at me, and you can imagine that long, long ago, once upon a time, I used to be a young man. In those days, we used to do all the scientific computing in Fortran. Formula translation is perhaps one of the oldest languages, and an amazing language if you love math, because when you write code, it practically feels like math. The way scientists write, let X be this and so forth. It's very, very intuitive. It does not have fancy features, but it is certainly amazingly fast. There's nothing faster, to my knowledge, than Fortran. Like, it beats C hands down. So a lot of the work that has been done for everything from ocean current physics, weather modeling, particle accelerators, the sort of work that I used to do, by the way. Many of you know that in a past incarnation, I used to be a theoretical particle physicist. So we used to do atom smashing, what people call colloquially, elementary particles, and the large had computations happening there in the colliders. And if you're looking at thermonuclear simulation and so forth, everything, most mission critical things, believe it or not, the underlying framework was done in Fortran. We still have, nowadays, you don't hear much of Fortran, but you'll be surprised to know that Fortran is still the leading workhorse of the computational world. It takes a long time for a library to perfect itself. Math is very subtle. When you convert math into code, it is not that easy. Because I'll give you a simple example, a pi. How many digits are there in pi? Infinitely many. It's an irrational number. Euler's number, Euler's constant, likewise, so forth. Computations are filled with irrational numbers, amongst other things. Now, computers, though, have finite memory. Any data type, float, double, int, short, long, whatnot, right? Int 32, etc., etc. These are finite boxes. You cannot store an infinite precision number in a finite box. You see that, right? And that leads to its own complications. How do you do that? So you have to stick to some level of precision. And you can't put too big a number. It won't fit in the box. So think about it this way. If you could write only 2 digits, well, you can't go beyond 99. I mean, if you take base 10, though it's usually binary, but to be intuitive, you can't run beyond 99. And the smallest number you can write is minus 99, isn't it? So therein comes the complication. What if you add 2 numbers and your total is more than that? So now I'll tell you how things get complicated. Suppose you have a number X and you have a number Y. How would you find the average of the 2 numbers? What's the average of the 2 numbers? So I'm just asking a question. If I give you X and Y, maybe, do you want me to write it out? I could do that. 2 numbers, X and Y. And if I asked you, how would you find the average or the mean of these 2 numbers? What would you do? Add and divide. Anybody disagrees? Sum is X plus Y divided by 2. How would you feel if I told you that that would be the most wrong way of doing averages? And can you guess why?
Because it's actually X by 2 plus Y by 2 average.
Are we missing the bracket? Like it's just Y in the bracket.
Or bracket? Yeah. So Ravi's thing is that why don't you divide X by 2 and then Y by 2, half it, and then add the 2, right? And the other is, why don't you put brackets? Brackets you can do. See, the problem is this. You are between 2 opposite perils. One is that if you do X plus Y first, you can have an overflow. X and Y, when they add up, may be beyond the capacity of the data structure, the data type. But you know that the mean has to be in between them. You should have been able to compute that. On the other hand, if you first divide, then you may have underflow. The numbers may be so tiny that if you divide, you're practically left with nothing. Are you seeing that? Right? So I will let you investigate what's the right way of doing it. But the point that I want to make is math is subtle. when you convert math to numerical computing, the bugs are subtle. It takes years to understand. This point, by the way, has a bit of a history. The Java language came around 1994, 95. It took many years. I believe it took almost a decade before somebody noticed that something that we all use, if you're using Java, the sort, that in the sort they had made exactly this mistake. And they had to re-implement that, fix that bug. And it just speaks to the fact that the way we think intuitively, the way we write equations on paper, and the way you have to convert it to code, in between is the reality of data types and their sizes. And you have to do it very carefully. And then comes optimizations. Suppose I give you two arrays, and I ask you, go do something with these arrays. Like, for example, add up these arrays. Your typical instinct would be, and I tell you that the two arrays are the same size, to write a loop. It's a really bad idea because it's not parallelizable, a lot of inefficiencies and so forth. Right? There are much better ways to add arrays. So all of those reasons put together, when you do numerical computing, people have created these libraries called BLAS and LinPack, LaPack, and so forth. It has taken years to mature those libraries, and they're near bug-free. Right? They're very, very stable. I mean, think about it this way. If you're looking for a library that pretty much determines a lot of the weather predictions, a lot of the literally national security level stuff, like simulations of thermonuclear fusion and things like that, or interactions in a particle accelerator, they are all resting upon libraries like this, Fortran libraries that have really matured over the years. And and to the best of our knowledge, don't have their subtle bugs. Now, the problem is to remove those kinds of bugs, it takes years of understanding. So when Python came out, when Python became a language for data science, for machine learning, it was very natural not to reinvent the wheel, but to say, one of the strengths of Python is you can do language binding to any language, like to C, to Java, to Fortran, and so on and so forth. The bindings to Java is there, but not very common. But yeah, to C and Fortran is very common. So what people did is they created bindings to BLAS and LinPack and LaPack. By the way, those of you who are familiar with MATLAB, it is nothing but, initially started out as nothing but a UI layer that just made it friendly. You didn't have to learn Fortran and gave a friendlier syntax over LinPack, LaPack. Right? Still, underneath it, those are the workhorses. So there's another reason to use these libraries. It's blazing fast. When you add in Python, first, Python doesn't have a notion of a high performance array. What you create is a list, and doing any kind of thing in list, you will see is rather cumbersome. Oh, for some reason, my LaTeX syntax has not come through in this. I have to figure out why. But okay, let's look at this. Imagine that you imagine simple Python. This is how you would create two lists. Imagine that the first list, you are a surveyor, you have gone around, looked at some plots of land, and you have made a list of the length of each plot of land. Then you made another list of the width of each plot of land. Okay? Just giving you a physical intuition. Then I ask you, okay, what is the area of each plot of land? You would either write a for loop to multiply it, or if you're a little bit more savvy with Python, you can use something called list comprehension. Do you notice that this is a list comprehension? Are we familiar with this? If you're not, see, list comprehensions is one of the lovely things about Python. But if you're not familiar with it, you realize that you could have just simply written it with a for loop. That's what it does. It's a nice syntactic sugar. So now you get the areas of it. Now you realize that this code and this intuitive way of thinking, length times width per area, they don't quite match, isn't it? The code looks far more complicated than the intuition. Would you agree, guys? Wouldn't it have been lovely if you could just do area is length times width, and you would automatically get an array in which you had the area for each of the plots of land. So that is what it is. It gets even more funny in Python. If I say find the, suppose you have to put fences around all the plots of land. You need to know the perimeter. So the perimeter formula is this. Length, there are two lengths and two widths. And so your perimeter would be this. If you try to do this, to your surprise, the result would be not what you expect. Because whenever you multiply an array by a number, it just repeats it that many times. So if you take this array, let's say the first array, 5, 2, 7, 9, 8, and you multiply it by 3, you're literally adding 3 copies of the array together to create one long array. Totally not what you would expect it to do. But for general purpose programming in the world of Python, it's a great convenience. One easy convenience is people often find a star and they want a line of stars. So they will make a encode star string and multiply, or line, a symbol, and then multiply it by 80 or something like that, or 100 to get so many so many lines there. Quite a good convenience for normal Python, but for computation it's a nuisance that it breaks all expectations like this. And if you want to do it correctly, once again you'll bring in list comprehension and you'll do something like this. Now it is not just not intuitive from a math perspective, it is also slow like crazy. You have Fortran, the fastest language on earth. And then you have Python, an interpreted language. Python, beautiful syntax, easy to understand. Everybody loves Python, but slow compared to for numerical. Like, let's just say that if you were to do all your weather simulation in Python, by the time you predict the weather for tomorrow, it would be August. I'm joking. No, I'm kidding. All right. So now you do just Python without using high performance libraries. So NumPy is a high performance library. We will take the same arrays, we'll make it into a NumPy array. So I put the prefix np underscore length. This is it. And see how intuitive it becomes. I say area is, does this line that I've highlighted feel completely intuitive, right? And it produces the right result. Likewise, the perimeter, does it feel very intuitive? It is that. And this, by the way, has deep consequences. PyTorch, the leading AI library for neural networks, has, as a deliberate choice, been aligned to NumPy syntax. If you know NumPy, you pretty much know PyTorch, a large part of PyTorch, the functions of PyTorch, right? Because of which, when you read the code for neural networks, or when you read the code for machine learning, one of the things that surprises you in this field is how short the code is. If you're used to general purpose business coding, which is reams and reams of code, right? And if you do UI coding, oh God forbid, right? Every page has like a huge amount of code behind it, right? Relatively, machine learning code is very tight, very compact, because a lot can be said intuitively and in a very brief form. This is one of the characteristics you will notice. You will see research papers published in our field and major breakthrough and so forth. And then they would have a GitHub. And when you look at GitHub, sometimes you'll find less than 200 lines of code, or just 100 lines of code. The main code, there'll be some extras here and there, but the core thing would be, sometimes it may be even less. They're just making an important point and it's a breakthrough. So the code in our field is actually generally much, much shorter than you're used to in general purpose programming. And it is very expressive. Like, for example, would you agree that reading this is a lot more expensive than the basic Python that we tried? Right? It is also super fast. The performance is very good. It gives you all of the benefits NumPy gives you, like indexing. So if you want to have the array and you want to know here, what is the first element, what is the second element, area. So here's the area. What is area is this. So if remember, indexing starts from 0. Right? So if I say area 1, I'm looking at the second element, which happens to be 4, isn't it? So 4. Oh, by the way, this mkdocs has mangled it. It was supposed to be the greater than symbol. So it just honors that mathematical notation. Area greater than 30 will automatically filter and tell you only those plots of land whose area is more than 30, right? And so it's saying, look at this. First one is not, second one is not, third, fourth, fifth are. Let's go verify that. You look at this, you can verify that that's true, isn't it? Likewise, you can even deal with mixed arrays, though I usually never do that. Now, two-dimensional arrays, what you call matrices, very simple. You have two-dimensional arrays, but you can have three-dimensional arrays, four-dimensional arrays, and so on and so forth. Right? In our field, you can have, you can have multi-dimensional arrays. Those multi-dimensional arrays, by the way, the formal word is tensor. They are tensors. Physicists call them tensors. Right? So any one of you who have taken college physics would remember your stress tensor, or if you have taken a course in gravitation, the gravitational tensor, and so forth. Now, if you get a matrix, here's the beautiful thing. This is why this NumPy is so liked in the field. You want to generate numbers on a bell curve. Now, there's something very interesting. In our field, we call the bell curve the normal distribution. The thing is, it could be the higher. So, for example, in 2 dimensions, a bell curve would be a bell hill. Right? Imagine a sand hill looking like a bell shape. Then higher dimensions. But general word that people use is it's a normal distribution. Right? And it's probably because it's the most ubiquitous thing that you see. You take lots of people, line them up by height, and you'll notice that it looks like a normal distribution. Though there are mathematicians who have disagreed with that. They would point out that it is actually a log normal distribution with standard deviation equal to 1, because a normal distribution will have negative values. Right? When did you find a person with negative height? You didn't. Right? So very strictly speaking, it is maybe a log normal distribution more appropriate, but in a very colloquial sense, yes, it looks like a bell curve. It's normal. Now, if you give an array, you can print, you can find out, you can do things like you can find out the length of the array, mean of the length, each of the arrays, right? You can do all sorts of things. You can find correlations. Are you familiar with mean, median, correlation between two sets of numbers, standard deviation, and sum, of course, everybody knows. The standard deviation. So you can print all of that. You notice that these are just simple functions and they come built in. That's the thing. So just about all the things that you do in your day-to-day life in computations come built in, which makes it very powerful. Now, here is the thing that is very interesting. You realize that you can do x plus y. In normal Python, if you do x plus y, it will concatenate the arrays, right? Or something like that. Here, you could do but here you could just do x plus y in array, just the way you think in math. You can do it like that, which is the same as this. And by the way, you're not just doing it with number. You can do it with a single number, which is called a scalar. You can do it with array. You can do it with multidimensional array. Are we together? Syntax is exactly the same. But what is more interesting is to multiply. Do you notice that we are not doing anything fancy, just putting a multiplication symbol, star, it will do the right thing. Multiply the arrays, element-wise multiplication. And if you want to divide one array by another, you can do x divided by y. You want to find the square root, you can do that. Oh, by the way, I missed the dot product. You can also do dot product between two numbers, like this. You can do the sum. You want to find the transpose of an array. What's the transpose of a matrix? Rows become columns, column become rows. Right? You can do that. By the way, when you say dot, there's something I don't know why I didn't mention it. Actually, there's an even simpler notation for doing x dot y. It is x ampersand y. Ampersand is a reserved operator for dot product. X ampersand y will produce dot product between two vectors. Right. So you want to produce a histogram. Suppose you create data, you choose data. This is called sampling of a normal distribution. Means there's a normal bell curve and you sample lots and lots of points from it, which means you take points, but points closer to 0 are more likely, right? Or whatever mean that you give is more likely. So here mean is mu and sigma. Those of you who are familiar with your high school bell curve would remember. Mu is what? Mu symbolizes the mean. Sigma standard deviation, exactly. So you're saying that give me data, 10,000 points from a normal distribution whose mean is 3 and standard deviation is 0.75. That's what you're saying here. From this, you generate the data. So D will be, what will it be? It will be an array of numbers. Now you want to do a histogram of it. we are using something called Matplotlib, you'll see in a moment. And it makes this plots, right? So plotting is also very easy. Do you realize that, guys? Imagine that you were doing it in JavaScript or HTML or something like that, or C code. You would be writing tons and tons, pretty lot of code. But here, all of these things usually come built in, right? One-liners. Most of the things you want are one-liners. Likewise, you can do plotting of sine curves, etc. So this is NumPy. Now, let's go to Pandas. What are Pandas? They give you basically a rectangular view of the data and a lot of manipulation facilities, functions on the data, right? So, oh, by the way, don't do pip install. Now, how would you do it with UV? I should update these notebooks. With UV, you would say UV add Pandas. You don't have to do it in this project, it's all done. Oh, by the way, I just noticed a bug. Those images have disappeared. I'll make sure that those images show up. There's a relative path issue. Yeah. So I think I could, okay, I'll look into it. So suppose you get data, it looks like this. Let's say that these are some weather station data, some ID of the station. Imagine Alaska, some date, 2010, 1st of January, 2010. And the minimum temperature was minus 178 and maximum was 311, based on some scale or unit they have, a Tmin, Tmax. Right, so this is how data comes, isn't it? It's a rectangular form, a spreadsheet of data. Given this data, you can check its shape, how many rows, how many columns. That's the first thing that you would ask, right? How much data do I have? How many rows, columns? You can get a sample of the first few items of the data is called head. And likewise, you can look at the last few rows of the data. You can say tail, right? I hope you are familiar with the head and tail commands in Unix. It gives you the same functionality. You can check the data types. It will tell you. Whenever you see object, it means it's a string. Date is an integer, and temperature, etc., is the integer. And then you can do all sorts of, I won't go into it because it will take us a long time, but suffice is to say that it comes with very powerful and easy way. You can ask it to describe the data. It will give you the entire descriptive statistics on each of the columns. Isn't that nice? If you want the Tmax, Tmin, the count, mean, standard deviation, right? A min, max, and quantiles are all here. Lovely, right? Given data, the first thing you would do is get the descriptive statistics on it. So you notice that the station and date columns are missing. So what you want to do, now it's getting detailed into Pandas, and I won't go in there, but there are ways to convert it into dates and so on and so forth, and get it as, then comes the rest of the data manipulation with Pandas, right? But let's not get in here into that, but that's Pandas. Then there is a data visualization library called Matplotlib. Now, Matplotlib has evoked a strong reaction from the community. It is the default visualization library that we all go to. But then lots of people say, oh, it's not beautiful, it's not good. So let's have better libraries. So there are lots of other libraries like Plotly, Seaborn. Seaborn is based on Matplotlib. People put layers over it. And then there are things like Altair, etc. So within the JavaScript world, there is a leading data visualization library called D3, which is a Michael Bostock's library, amazing library. Now, with that library, on top of library, people have put additional layers to make it easier to write D3 code, things like Vega Lite, etc. And Altair is the Python layer on top of all of that, right? So it's a tower. First you have D3, then you have Vega Lite, then you have Altair. So Altair makes it very easy to write code, which is interactive like D3. There's interactivity. Plotly is a library which also has a commercial side to it, but it's open source, where again, you get Python syntax, but it produces interactive plots because it's based on D3 under the cover. Now, having said all of that, Matplotlib still remains the default library for plotting because of its utter simplicity. Right? And this is it. So suppose you have data, X and Y data, and you want to plot it. Do you see how simple it is? You want to make a scatter plot. Can you think of a syntax simpler than this? plt.scatter, right? Give it the X part and the Y part of the data frame and the columns, and it will do it. You can now also Matplotlib is built into the Pandas now. So you could just go to the Pandas data spreadsheet and say, go plot me a scatter plot. And these are the columns you will use. It will do it. There are all sorts of alternate syntax that you can use. You want a histogram, just say hist. You see how easy it is, guys? .hist. You'll get your basic visualizations quickly. Right? And then there are other libraries like Bouquet is one more library. Then, so my go-to usually is I tend to oscillate between plain Matplotlib and Plotly. Right? So if you look at Matplotlib, and so everybody's personal choice differs. Right? So pick your favorite library. Matplotlib is the default. Now, one of the things people say that if you want to publish a research paper, the default, like you can't send, if you send this plot to a research paper, it will be turned, like you'll immediately get criticism from the reviewers, people who are reviewing your paper. Some things are glaringly missing. Can you point out what is missing in this graph?
There's no title, no.
Exactly, no title. You don't know what the x-axis is. You have no idea what the y-axis is. Nothing is mentioned. So you can do that. Now, all you have to do is you can set that. Let's do that. You notice that adding some styling to this. Now, here is a beautiful thing. There is a language for typesetting math, for writing math. It is called TeX. And its easier version is called LaTeX. So do you see this weird symbol here? $math BF, blah, blah, blah. Anybody? If you have been doing mathematical, those of you who did graduate work or published some paper, must be very familiar with it. Most of us are not. So it is called LaTeX or LaTeX. Some people call it LaTeX or LaTeX, right? It is a markup language, just like HTML. It's a beautiful mark. If you have never used LaTeX, I would say, strongly suggest, become familiar with it. All the research papers that you are reading from archive, etc., most of them are written in LaTeX because it gives you a facility to write mathematical expressions beautifully. And basically, text comes out better. Let's put it this way. I almost have never written documents. In fact, I have never, unless forced to edit somebody else's document, I've never used one of these tools like Microsoft Word or Google Doc or whatnot. I have only 3 things I use. Markdown, which is easy and nice, or HTML. Next level is, I notice there's some sophistication it needs. But if I'm writing something formally, there is only one thing that I use, ever. If it is a formal document, it will be in LaTeX. Always write it in LaTeX. And those of you who are going to come next week to my, or this weekend from onwards, to the formal sessions, the 4-month-long courses that I'm giving, you'll get a lot of those well-printed documents. But anyway, we will just pay attention for a bit to this. Do you notice that when you do it like this, plot, I'm giving it X label, Y label, title. But do you notice that in the title, I've inserted some mathematics just for fun? It's not a linear relationship, by the way. This is wrong. This title is wrong. It is a sine wave. It is a non-linear relationship. So I should have been careful not to give this title. But I have given the x-axis and the y-axis here. If you look carefully, those things are marked here. So a little bit better. You can make it even by, oh my goodness. Again, I made the same mistake, calling it a linear relationship. I apologize. It's not a linear relationship. So it looks more like a sine wave. Right? So do you see, guys, you can do, you can play around with things. You can even add annotations. Oh, look at that. If you are explaining something, right? Like here, I'm explaining something very, I just for the sake of illustration, I said, you will see, oh, now I fixed this title. Much better, isn't it? The title is fixed. There seems to be a sine wave. This happens to be the equation of a sine wave. And here, you put annotations. These are called annotations. How did I do that? Let's ponder over this code. This part is easy, scatter plot XY. But notice how much aesthetics I added. I changed the color to salmon. salmon makes it prettier. Do you guys like this color a little bit better than just dark red and dark blue or black, right? So that is it. You can do all that. Now I said markers are O, that is okay. Alpha, what does alpha give you? Transparency. It just makes it look sweeter, nicer, in my view. So do you feel that this salmon color is a little bit better, right? And then line width is 8. So there's a, anyway, that may not be. Then the title, etc. are given here. Why, well, I don't know, PLT title. Now I've given an annotation. This title is wrong. I mean, this gets overwritten, fortunately, by the correct title here. This plt.annotate creates an arrow. Note the curvature point here at this. It is this arrow, and likewise this arrow. So those of you who know, who have done a lot of data visualization or plotting, you know that it is easy to do that. It's just that you start simply and add piece by piece to that, right? So where did we start? We started with this one-liner, and then you develop that slowly, isn't it? You develop that, and soon you become, when you become good with this, any library like Matplotlib itself, when you become good with it, you realize that you can create as pretty a plot with just Matplotlib as you could get with any fancy library, right? And it is publication ready at that moment, right? How do you create subgraphs? There are ways to do subgraphs. There's a bit of syntax for it. I won't go into that because in a data visualization course we do that. By the way, that's another free course we offer when we next offer, if you're interested in good data visualization practices, do that. See, visualization is a language, just like spoken language. And if you treat it as a formal language, then there is a grammar behind it. It's called the grammar of graphics. And there is a structured way of building up visualization, so that if you follow that structure, invariably, you'll be able to systematically create evocative, beautiful, complex visualizations. That's a subject in itself, but we won't go here. Suffice it to say that it gives you the ability to create subplots. You can do histograms and so on and so forth. And so with that, I hope I've given you a very quick introduction to NumPy, Pandas, and Matplotlib, guys. Would that be enough? So read this thing. I think if you just sit quietly and read this, we have put enough text here that you will hit the ground running after that.
I just want to comment, the data visualization course is very engaging. You'll see this like for Matplotlib. Go to the second part, you'll say Kyle's like for Altair.
Yes.
But Matplotlib gives you a lot of flexibility, which SIP uses to full extent. I would say it's the master. He will make you fall in love with visualization. It's worth in a second.
Yes, thanks. Thank you. Thank you for saying that, Sanjay. So, all right, guys. So I will stop here.